Tschurtschenthaler.
Thank you.
Ich hoffe, ich habe es richtig ausgesprochen.
Fantastisch, sehr gut. Vielen Dank.
Willkommen.
Thank you.
Bitteschön.
Thank you very much. Merhaba and welcome also from my side. I'm very happy to be here today and present you on how we can support you on your journey of the cement industry towards net zero emissions. ABB has a long history of serving the cement industry with solutions ranging from full turnkey electrification and automation projects to distributed control systems, and also with our set of tailored digital solutions applicable for the cement industry, helping to optimize the process and running the plant smoothly. Now, if we look at our portfolio of integrated solutions for the cement industry, we start at the high voltage substation, where we can optimize the integration of various different sources of electricity, still allowing you to have a stable and continuous power distribution to your different plant areas. Then our drivetrain solutions for fans, kilns, mills, and coolers all run at highest efficiency, reducing the overall power demand of your plant. And then with our distributed control system and our high-performance HMI, we enable the plant operators to act efficiently and swiftly in case of abnormal situations in the process, and by that reducing the overall potential downtime of your plant. Our aim is to support the cement industry across the whole project life cycle of a project, starting already early on at pre-feasibility, feasibility study, where our set of very experienced engineers can help you to optimize the design and the cost of your electrical and automation infrastructure, and by that reducing your overall cost of your project. And this is then carried on throughout manufacturing and execution, and most importantly also during operation, where our service teams can help you to keep your plant running. Now at ABB, we are committed to support the cement industry on the journey towards net zero and reach the targets of the Paris Agreement. And for this purpose, we have actually started to develop specific solutions targeting at reducing the carbon emissions in the cement industry. Like, for example, with our expert system, the Expert Optimizer, which is basically an advanced process control system for which we have developed specific cement-specific modules, reducing the overall electrical and thermal energy requirement and allowing you to maximize the utilization of alternative fuels in your process. With the implementation of such an expert system, you can reduce the footprint, the carbon footprint of your operation of an average cement plant by approximately 100,000 tons of CO2 per year, which is quite a significant amount. Another approach we are taking in the field of removing the need of burning of fossil fuels in the process. Here we are working with a highly innovative startup company called Coolbrook. Coolbrook has developed the so-called rotodynamic heater technology. So jointly, we have decided to build solutions for the cement industry targeting to remove the need of burning of fossil fuels in the cement process through this technology, which allows to produce process heat up to a level of 1,700 degrees, fully electrified. This technology has a lot of advantages, like you can use it in different temperature spaces, so from 400 to 1,700 degrees. Also, the way the heat can be applied into the process is very flexible. You can do direct heating, but you can also do it via heat exchanger. Or since it is actually based on a rotating equipment, you can also use it as a hot gas blower or just a hot gas generator. So there are many positive aspects about this technology. Now I believe today there are quite a number of engineers sitting in the audience here, so I think it would be good to explain a little bit on how this technology actually works. So it all starts with electricity, if possible with renewable electricity. The electricity is fed into an electric motor, so we convert electricity into kinetic energy of the rotating shaft of the electric motor. The motor then drives the rotor of the rotodynamic heater, on which we have installed outside of the rotor blades. We can see that on this picture demonstrated there. These blades accelerate air to supersonic speed and therefore convert the kinetic energy of the rotation of the motor into kinetic energy of the air. The speed up air. When the air then exits the diffuser, it is decelerated very rapidly. And at the moment of deceleration, the kinetic energy of the air is converted into internal energy of the air, which is heat. So basically, by passing air through one stage of such a machine, you can heat up the air by approximately 150 to 200 degrees. Now, if you need higher temperature, you just add additional stages of the same time. So you can repeat the same increase of 150 to 200 degrees across each and every stage. So actually, you could do that infinitely. The only limit is actually the material of the machine itself, which at some point, at some temperature level, starts to become soft. Now, just recently, a couple of weeks ago, the rotodynamic heater technology reached another milestone. And this milestone was that we crossed with this machine the temperature level of 1000 degrees successfully with our test machine located in the Netherlands. I mean, you can see on this picture, this red color there, that's not paint, that's the rotodynamic heater glowing at 1000 degrees. Now, if we look a little bit into the future, how can this technology be applied for the cement industry? Well, there are a couple of, let's say, low-hanging fruits, like drying of raw material or drying of alternative fuels before it goes into the process. But then also topics like calcination of clay could be done with the status of this machine today. So you could start with implementation today. Then looking a little bit into the future, the next 1-2 years ahead, we are already working on designing a solution which can replace the need of burning of fossil fuels in the pre-calciner and replace it with a solution based on the rotodynamic heater solution. And then looking into a bit further future, our aim is basically to reduce the need of burning of fossil fuels as much as possible in the cement process. It will likely not be possible to completely remove it with this technology, but at least we can help to co-burn or co-heat also on the main burner side of it. Another topic we are working in relation to carbon reduction is on the field of the mobile heavy vehicle fleet. So if we look at this study from McKinsey, it shows us that battery-heavy vehicle, but battery-based heavy trucks are already going to be cost competitive in the very near future. In 2 to 3 years, it's not going to be anymore a decision purely for the environment, but it's also going to be a commercial decision as well to move your heavy vehicle fleet towards electrical. And for this purpose, we have designed charging infrastructure, a high-power charging infrastructure which runs fully autonomous. It allows the charging of heavy vehicles on a quarry or mining site fully autonomous without the intervention of any human being. So if we look at the concept which we are applying here, so it consists basically out of two modules. The first one is the electric charging module, where we have installed all the main electrical components like the charger itself, some switchgear, and also the main controls are located in this first container. Then we have cables connected to the connector terminal unit. This connector terminal unit consists basically of the pin, of the charging pin, which then connects to the truck. This charging pin is protected with a cover in order to be possible to install it outside in the field on a quarry site where you have a very rough environment, you have a dusty condition, and with this protected device you can make sure that you don't create issues during operation. And this pin is also mounted on a mobile platform. You might have different types of trucks running on your plant, and each of the trucks might have the position of the charging socket on a different location. And in order to adjust to that, the pin is mounted on this mobile platform in order to adjust before charging can start. Now we can look at a small video of our pilot installation in Canada. Here, a 60-ton truck arrives at the charging location. So before arriving to the charging location, the truck communicates digitally with the charging station, announcing that he's arriving and he has the charging position of your socket, of his socket, at a certain position. The mobile platform adjusts itself and starts the charging cycle. When the battery is loaded, it disconnects, all fully autonomous, and the truck can go its way. So as you can see from this video, there is no need for any human to do any activity in order to charge your truck. So this allows you also in the future to run your trucks fully autonomous, since you can also remove basically the driver out of the truck. And this is not only good for the environment, but it's also good actually from an HSE perspective, because you remove people, human beings, from potentially dangerous zone on a quarry or a mining site. Now we have seen there are quite a number of technologies out there which can help to reduce the carbon emissions on a cement operation. But if we look at the roadmap towards net zero of the Global Cement and Concrete Association, we see that there is one technology which stands out, assuming to take the biggest chunk of the carbon reduction in the future. And that's carbon capture, utilization, and storage. And that makes a lot of sense. I mean, in the cement process, even if we remove all of the burning of fossil fuels, you still have the portion of CO2 emitted from the limestone itself during the calcination process, which at some point we need to handle. And that, at least from today's point of view, is only possible with carbon capture technology. Now, implementing carbon capture on a cement plant brings a lot of challenges with it. I mean, when you implement carbon capture at your plant, you will realize your electricity demand will potentially triple, quadruple even. So can your infrastructure cope with that? Then you will require also steam and cooling agents. Is your plant prepared for that? So there are a lot of topics which need to be considered when you decide that in the future you would like to implement carbon capture technologies at your site. And for this purpose, we have decided to make a partnership with a company called Captimize. Captimize is a Swedish-based company with a lot of experience in the field of various different carbon capture technologies. They have more than 15 years of experience in executing projects in this field, both in Europe but also in the US, in various industries. And their knowledge on the carbon capture technologies and our knowledge on electrification and automation and the related infrastructure, with this we would like to provide to the cement industry a service to carry out pre-feasibility and feasibility studies, technology independent, allowing you to take the right decision for your specific plant. Now let's look at the business case of carbon capture technology. It's a bit of a complex business case, as there are many items which need to be considered along the value chain. So it starts with the capture unit. Today there are quite a number of different technologies around on the market, so you need to screen out which one fits your specific plant and your needs and your schedule best. Once you have captured the carbon, you need to process it, you need to liquefy it. Liquefying this gas needs a lot of electrical energy. Is your infrastructure prepared for that? How do you deal with this? Do you need to build additional power sources like solar or wind in order to cope with that? And finally, you need also to understand on what kind of transportation means are you going to utilize once the carbon is liquefied. Are you going to deliver it by truck, by train, by ship? Eventually you're lucky and you have a pipeline which you can utilize. Or in the best case, even you can actually utilize the captured carbon to do something valuable, like for example, renewable aviation fuels. So all these topics need to be considered before you actually go into a project on the carbon capture side. So when Captimize and ABB starts with a feasibility study for a CCS implementation on a cement plant, we would first ask you one question. When do you plan to start your facility? Because this has a very big effect on what kind of capture technology might be suitable for your specific case. As said, there are many different types of technologies around on the market today. They might be, proven in some industries, but are they efficient? There are a lot of novel technologies as well, which promise to be more efficient, but are maybe at a lower TRL level today. So depending on your project schedule, when you would like to go online, you might choose a different set of technology which you look at more in detail. So once you have taken that part of a screening first, we would start with analyzing what kind of power demand, what kind of steam and cooling demand is required for those selected technologies. And already there, you will likely see that you will not be able to implement a full-scale implementation of a carbon capture unit for your plant, because likely you do not have enough power available on your site, or you will not have enough steam available on your site, or maybe even both of it. So you will have to reduce and scale your first implementation unit to what is possible and feasible at this specific stage. Once this is done, we would do a preliminary costing, both on the CapEx and on the OpEx. On the CapEx, the main drivers are things like how are you going to implement your project? Is it going to be turnkey EPC, or is it going to be an OEM approach where your own engineers work on it as well? On the OpEx side then again, the technology, the capture technology is driving a lot on the cost side. There is different costs on energy requirement for the different technologies. There is different costs related to the solvents. So all of this needs to be calculated. So once this is done, We will present you the full costs of it, CapEx, OpEx, for the selected technology to allow you a fair comparison and allowing you to take a fact-based decision on which technology you should move forward with. And once you have selected a specific technology which you would like to implement, we can also provide you with the opportunity to implement a test and pilot unit together with Captimize. So Captimize has the experience of building these small test and pilot units directly into the process, which can be used to do a proof of concept of your technology, of your selected technology. But it can be used also to train your staff before you go into the implementation of a full-scale CCS unit. Your staff needs to understand how to handle the solvents, how to handle the gases. It's everything a little bit different compared to handling solids like the cement industry is used today. But maybe one of the most important topics is actually the public relation. If you install such a pilot unit on your plant, you communicate to the outside world that you have real intentions. And you will see that this will provide you with a lot of positive feedback and most probably also quite a lot of interested visitors who want also to understand how to move forward with carbon capture on their sites as well. Good, and with this, I would like to conclude. I hope I've been able to provide you with some interesting views on how to reduce carbon emissions on the cement industry and how we can support you there. If you have any specific questions on carbon capture and the relative technologies, today we have also a representative from Captimize here with us, so you can please come to our booth and we can discuss whichever thing you would like to discuss. Good, and then with this, that would be it. Thank you very much.
Thank you very much, Mr. Tschurtschenthaler.